าสตราจารย์ดักลาส ดี โอเชรอฟได้รับรางวัลโนเบลสาขาฟิสิกส์เมื่อปีค.ศ. 1996 จากการค้นพบความเป็นของไหลยิ่งยวดในธาตุไอโซโทปฮีเลียม 3 ถือเป็นการค้นพบที่เป็นประโยชน์ต่อวงการวิทยาศาสตร์เป็นอย่างมากและก่อให้เกิดการศึกษาและวิจัยด้านของไหลยิ่งยวดซึ่งมีประโยชน์ในการศึกษาปรากฏการณ์อื่นๆในธรรมชาติเช่นการศึกษาการก่อตัวของกาแล็กซีในยุคเริ่มต้นของจักรวาลปัจจุบันศาสตราจารย์ดักลาส ดี โอเชรอฟอายุ 67 ปีเป็นศาสตราจารย์สาขาฟิสิกส์มหาวิทยาลัยสแตนฟอร์ดซึ่งในครั้งนี้ท่านได้ให้เกียรติมาบรรยายเรื่องความก้าวหน้าทางวิทยาศาสตร์เกิดขึ้นได้อย่างไรและวิทยาศาสตร์เปลี่ยนชีวิตเราอย่างไร
I'm promised to give you a talk today, and I'm hoping you'll find it interesting. Okay, so this is the Grand Canyon at sunset, and what I wish to say is that those discoveries that most change the way we think about nature cannot be anticipated. How then are such discoveries made, and are there research strategies which can substantially increase one's chances of making such a discovery? And of course, I have to think the answer to that is yes, or I wouldn't have asked the question. So let me illustrate this with a linked chain of discoveries and inventions, starting with one of my great heroes, this gentleman here, and I presume that everyone knows who this is. This is Heikki Camerlionis, who was the first person to liquefy helium, and I dare say without his contributions, I probably wouldn't be speaking here today. Camerlionis first liquefied helium in 1908. This was helium-4, the commoner isotope of helium, although helium is not very common. In just 5 years later, he received the Nobel Prize for Physics. And I suppose you can imagine that he's smiling at us, but in fact, I don't think that Camerlionis, I think he seldom smiled. So what happened was that there was a competition between Dewar and Camerlionis to see who first could liquefy the lightest and most inert of the atmospheric gases. And it looked like Dewar had won when he succeeded in liquefying hydrogen. Of course, hydrogen is the lightest element, but it's certainly not the most inert. So Camerlionis, there was only one element left to liquefy, and that was helium. Helium was very scarce at this time, but eventually Camerlionis was able to get enough helium that he could attempt to liquefy it. And Camerlionis decided to answer some other interesting question of the day that he could with this very spectacular set of refrigeration devices that he had built. People were arguing about what would happen to the conductivity of a very pure metal if one could cool it to absolute zero. One school of thought was that as you cooled it, you eliminated the lattice vibrations that scattered the conduction electrons, and so gradually the electrical resistance would slowly drop towards zero, whereas the other school of thought believed that at some temperature the conduction electrons, which are free to roam around the interior of the metal, would recondense on the ions from which they had come, and all electrical conductivity would cease. So Camerlionis obtained a very pure sample of mercury and gave it to his associate. I actually don't know if Gilles Holst was his graduate student. Camerlionis was not of the habit of including his students' names on his research papers. So it's a little bit difficult to tell, but so I hear some hissing in the audience. It must be a graduate student's hissing. Anyway, so Gilles Holst is measuring the electrical resistance. Those are the green points. This is the scale of resistance from 0 ohms up to 2/1000ths of an ohm, very small resistance, electrical resistance. And temperature goes from 4 Kelvin to 4.5 Kelvin. And as you can see, as he is cooling it, in fact, the electrical resistance is dropping. But then at a temperature of about 4.2 Kelvin, there was a nearly discontinuous drop in the electrical resistance to a value that was less than 10 to the minus 5 ohms, essentially zero electrical resistance. This, of course, we look at this and we now know that this, in fact, was the onset of superconductivity. The metal that Camerlionis had given Geelholz was mercury, which is a very good superconductor at low temperatures. So, in fact, this was the first observation of superconductivity. And I don't know if this is exactly what Camerlionis got the Nobel Prize for in 1913, but I suppose it had something to do with that. I dare say that superconductivity has been studied in multiple places around the world ever since that time. It's a phenomenon that has fascinated physicists for a long time. So now you see what I actually am is not a physicist, but a photographer. This is a small part of the Iguazu Falls at the border between Paraguay and Brazil. And I like to illustrate the ideas in my talks with distracting photographs in the background. So the process of advancing science often leads to inventions and technologies that directly benefit mankind. However, it is impossible to know from where the advance will come that might solve a particular problem facing mankind. Consider, for example, nuclear magnetic resonance. And I don't mean to say that nuclear magnetic resonance is a problem facing mankind, but a solution to problems facing mankind. So nuclear magnetic resonance were invented by these two gentlemen actually in 1946, just at the end of World War II. The two gentlemen are Felix Bloch, who was a professor at Stanford University. And I dare say Felix Bloch was a rather crusty old man. Even though I'm a professor at Stanford University, I never met Felix Bloch. He died by the time I became a professor there. Ed Purcell was a professor at Harvard and a very kind and gentle and warm person whom I dearly loved. And I'm afraid he's not around either anymore. But these were the two gentlemen that invented NMR. And so, of course, they got the Nobel Prize just 6 years after their development, their invention, and so they went to Stockholm and got their Nobel Prizes. And, of course, then the press descended on them. Of course, they were asking these gentlemen to explain nuclear magnetic resonance, which is a very complicated process involving the precession of nuclear spins having magnetic moments and magnetic fields. And after a while, the press would give up because they couldn't understand any of this. And so they said, just tell us what NMR, nuclear magnetic resonance, might be good for. And Felix Bloch is supposed to have said, damn little. His idea was that they were measuring the distribution of charge into atomic nuclei, and this had nothing to do with applications. And Ed Purcell, who was a kinder, gentler man, said, well, perhaps one can use nuclear magnetic resonance to calibrate magnetic fields. Now, this is what the visionaries that invented NMR had to say about it. Let's see what actually transpired. Well, first of all, this is a spinning top in a gravitational field, and this is basically explains what Felix Bloch and Ed Purcell couldn't explain to the press, but so I think we can blip over this. And now we're looking at an organic molecule in solution, probably aqueous solution, and specifically we're doing nuclear magnetic resonance on the hydrogen nuclei, the protons, and what one finds is in fact that they did all the protons, the hydrogen atoms, do not come into resonance at the same time. There are triplets and quadruplets depending upon just exactly which hydrogen atom you're looking at, and it has to do with these bond processes. But basically this was, in fact, if you look at the scale here, these are frequency shifts in parts per million. These were very, very tiny effects, and it really took quite a while to be able to do this, but in fact, this was a spectacular advance in nuclear magnetic resonance at that point. I dare say that the thing that really made this work was in fact not doing what's called continuous wave nuclear magnetic resonance, where you either swept slowly the magnetic field or the frequency, but in fact this was pulsed NMR. Pulsed NMR was invented by this person here, Richard Ernst. Now, it used to be that there were a set of meetings every 3 years, I believe it was, and I would meet most of these gentlemen. So I met Richard Ernst. What Richard Ernst did for nuclear magnetic resonance, he is rather than very slowly tickling the nuclear spins, in fact, he would apply a very intense pulse of RF energy, which would tip all the spins by 90 degrees, and then as they processed, they would induce a voltage in a pickup coil, and that's pulsed NMR, and that's, in fact, what Richard Ernst got the Nobel Prize for in 1991. It wasn't in physics. Physics was the original NMR Nobel Prize, but in chemistry, because, in fact, this was mostly useful for organic chemists in particular. That Richard Ernst didn't do this all by himself. He had a partner, and his partner's name was Kurt Wutrecht, and the two of them had done a lot of this work. But when it came time to getting a Nobel Prize, in fact, Kurt Wutrecht did not share the Nobel Prize with his Swiss colleague, Richard Ernst. And so I would meet these guys at these NMR meetings, and I went to Kurt Wutrecht and I said, Kurt, how did you feel when Richard Ernst got the Nobel Prize and you didn't share it with him? You must have been disappointed. He said, no, I wasn't disappointed. I was mad. And so, but it's interesting. What happened, of course, is that Richard Ernst then set out as a man possessed to show that he could do things with NMR that no one else could do. And indeed, he invented a very complicated pulsed NMR sequence which allowed him to determine the three-dimensional conformation of even complex molecules like proteins. So this was a real boon to NMR, and of course, eventually in 2002, Kurt Wutrecht got his own Nobel Prize, and if you look, he's smiling. I think you can't be accepting the Nobel Prize from the King of Sweden without smiling. Anyway, so now we've had 2 Nobel Prizes in chemistry for aspects of NMR, and a Nobel Prize. The original one was in physics. But we're really not done yet, because in fact, I think, I don't know, I was probably not the first one, but people in the early 1970s started realizing that if you applied a magnetic field gradient across the sample which contained the nuclear spins that you wish to study, that in fact you could actually create images with very detailed structure. This is a rather healthy human knee. My right knee is made of titanium, and I don't think you can do those experiments on it anymore. Anyway, so for their work on developing what's called magnetic resonance imaging or nuclear magnetic resonance imaging, Paul Lauterbur and Peter Mansfield in 2003. Now, this is 1 year after Kurt Wutrecht got his Nobel Prize for determining the three-dimensional conformation of very tiny things, proteins, and these two determined the three-dimensional conformation of large biological things like knees. They shared the Nobel Prize the next year. This is the 4th Nobel Prize for some aspect of nuclear magnetic resonance. And if we go back now to what the inventors at NMR said to the press, Felix Bloch, when asked what NMR might be good for, he said, damn little. And of course, his counterpart said maybe one could use NMR to calibrate magnetic fields. And so what I'm trying to show you is that the visionaries that developed these new techniques don't necessarily know what they might be good for. And I think that's something that's worth remembering. So this is, in fact, Felix Bloch again, and this is Ed Purcell, and we're back in 1952. And I would like to think that Felix Bloch is smiling a little bit in that picture, but I think I'm not sure. He should have been alive by the time that prize came out. Well, now I'm going to really shift gears and talk a little bit about my own contributions to science. And I suppose the person that I have the most to thank was my chemistry teacher, shown right here. This is William Hawke, and I dare say that the first large prize I got was a MacArthur Prize. And I called him up on the phone, and I said, I hadn't seen him for many years, and I said, Mr. Hawke, guess who? And he said, well, that has to be Douglas Osheroff. I think he'd read that I'd gotten this prize and thought I might call him up. Anyway, so this is William Hawke, and this guy that's looking over his shoulder, that's me. I dare say that the next three people, these were guys that we were partners in crime. We liked to make bombs and rockets, things like that. So we did a lot of that sort of thing. This is Al Close, who was my debate partner in high school. I was not a very good debater, I'm afraid. I didn't do my homework well, but we managed to win our share of prizes, I suppose. Okay, so then I'm blipping over my 4 years at Caltech. I actually was involved in astrophysics when I was at Caltech, mostly. Infrared astrophysics was a new field, and so when I applied for a graduate study, I actually applied only to schools that had good astrophysics programs. And then, as I was, actually I think I applied to 8 schools, and I got accepted to all 8 of them. But then I started thinking about what I loved doing with my life, and it wasn't observing some objects that were so far away I couldn't possibly touch them. But in fact, I really liked to do experiments. And so in the last moment, I switched, and I decided to go into condensed matter physics, as you heard. So I went to Cornell, and that as a graduate student, and I was teaching for David Lee, who ended up being my PhD thesis advisor. And this was just at the time that new refrigeration technologies were being developed. So this is something called the helium-3, helium-4 dilution refrigerator, and I won't explain all of it. This is actually a picture of my helium-3, helium-4 dilution refrigerator. This is where the cooling occurred, and then these are heat exchangers which would use the rising cold helium-3 liquid to cool a returning helium-3 returning to the mixing chamber. So this was my device, but when I was at Cornell at that time, every graduate student was building their own dilution refrigerator. Mine was one of the ones that actually worked, which was a good thing for me, anyway. So, but in fact, there was another technology. So what had happened was helium-3 and helium-4 are, of course, both isotopes of helium, but helium-3 is extremely rare. It essentially doesn't exist naturally. The amount of helium-3 in natural gas wells, which is where you get most of the helium-4 from, was vanishingly small. However, helium-3 results from the decay of tritium. And so during the period after World War II, where the US and the Soviet Union were busily building hydrogen bombs, they were creating tritium, and tritium decayed into helium-3. There was a guy named Ed Hamill at Los Alamos that was responsible for keeping their tritium supply clean, and that meant sorting out the helium-3. And then, without getting permission from anyone to do this, he decided that he would liquefy the helium-3 and measure its vapor pressure as a function of temperature. And he did that, and he published the results. And not only did he publish the results, but he said how much helium-3 he had. That told the Russians something about how much tritium the United States had. But he didn't lose his job. I interviewed him. He was 81 years old. It was a telephone conversation. And I wish I'd met him because he was a very colorful character. Anyway, there was a Russian theorist at who was a member of what's called the Landau School, with very broad interests. And when he heard about helium-3, he started thinking about its properties. Now, helium-3 liquid at low temperatures, the entropy or disorder drops linearly to 0. So this is the entropy of liquid helium-3. Solid helium-3 is perfectly ordered spatially, but each nuclear spin can point either up or down in a magnetic field. That gives you an entropy of R log 2. And so below the temperature where these two curves cross, you have the very unusual situation in nature that the liquid is more highly ordered than the solid of a substance. I think this is the only case where that actually happens. And then Isaac Pomeranchuk was the Russian theorist, realized that so the helium-3 has a negative melting curve because of the fact that these two cross. And if you start with liquid helium-3 and you compress it and you start solidifying it, as you move along this melting curve, you move to lower and lower temperatures. So this was a technique that people predicted would allow you to reach temperatures probably less than 1,000th of a degree above absolute zero. And as a young graduate student, I said, I want one of these things. And so we had enough helium-3, and I built a very elegant, this is my Pomeranchuk cell, as it's called. So this gold region is helium-3 because it's rather expensive, I suppose. And the idea is you push metal bellows in here that decreases the volume and raises the pressure until some of the liquid starts converting to solid. And for every % of the liquid that converted to solid, the system would cool by 1,000th of a degree. What that meant was that if I converted 15% of the liquid to solid, I would be at a temperature very close to absolute zero. So that was the technique which I was pinning on my hopes on in order to get a PhD out of the low temperature group at Cornell. So here, in fact, is some data. Now, this is taken, you have to explain these things because young people now don't understand strip chart recorders. So the paper moves underneath a pen, which moves back and forth according to what voltage is applied to it. And so, in fact, this is the melting pressure of the helium-3 as it's cooling. And I'm actually measuring a pressure transducer made with a capacitor. So this is actually the capacitance, and I rebalance the bridge, and it continues to cool. And then there was a very sharp decrease in the rate of cooling, which I later labeled it A, but I was in fact quite crushed to see this because I felt that something had gone wrong. And so I let this continue to cool. And then I saw a little tiny drop in pressure at, I wasn't very, shall we say, creative. I didn't give these things good names. A and B is what they were called. And in fact, this is the A superfluid, and this is the B superfluid, helium-3. So those names have actually stuck. But this was done this was actually not the first time I'd seen these things. I went back and looked at my old data, and there they were. So it was actually the pressures where these occurred were very highly reproducible. And so I suddenly realized, in fact, that, you know, this is something really, really exciting is going on. And so let me see if we have it. I invented a form of MRI where I actually applied a horizontal magnetic field that was larger at the bottom than the top. And so then if I applied an RF frequency, I would get a resonance layer such as I show here in red. And if I swept that frequency upward, this resonant layer would move down. So I could actually measure the NMR properties of the mixture of liquid and solid helium-3 as a function of position inside my cell. And so these are what some early data looked like. This is all liquid. There was this funny feature here was because the pressure transducer itself was slightly magnetic. And then we start cooling, and this is solid helium-3 started growing, and it gets larger and larger. And I have to change the gain, so the liquid looks like it's getting smaller, but in fact it's staying the same size. So this is real data. This was taken on April 17th, 1972, and I was looking at this data later on, while I was waiting for things to happen, and this is the liquid signal, should have been flat across here, and it looked rather badly distorted. And so I knew exactly what that meant. I wrote in my lab book, oops, yeah, here we go, 2:40 in the morning. This is a very good time to do research. No one bothers you at 2:40 in the morning. There's less radio frequency interference, there's less vibrations. It's the time to do research. So I wrote in my lab book, have discovered the BCS transition in liquid helium-3 tonight. And BCS is the theory that explained superconductivity. Bardeen, Cooper, and Schrieffer are the three theorists that did that. And people had predicted that helium-3 might undergo a similar phase transition, but it had never been seen. So there it was at 2:40 in the morning. What could I do? I ran around the basement of the physics building to share this exciting news with other graduate students. Well, it turns out no one was there. So in desperation, I went up to the 6th floor. The theorists, you see, like to be as close to God as possible. So they in fact would normally inhabit the 6th floor, but it turns out on that particular night there was no one around. And at 4 in the morning, I couldn't stand it any longer. I called up my thesis advisor, Dave Lee. Now, there are young people in the audience, so let me say that you do put your life in your hands if you call up your thesis advisor at 4:30 in the morning. However, in this case, David Lee called me back at 6 a.m. He'd not been able to get back to sleep, so neither one of us got any sleep that night at all. Anyway, I wanted to share this because it's I suppose not typical of the way science is done, but you get some feeling for the excitement associated with discoveries. So here I have some strategies, and this is really from another talk, but so utilize new technologies to view nature from a new perspective or a different realm. Now I'm talking about MRI, using the magnetic field gradient. Don't give up when things are going badly. Failure might be an invitation to try something new. Now, I didn't tell you this, but to do the NMR experiments, I obviously needed a magnetic field, and the magnet that produced that field weighed about 5 tons. And we only had one of them, and some other students had gone to David Lee and complained that I'd been monopolizing this magnet for quite a long time. It was only, and then Dave Lee told me I had to give up the magnet, and so then I felt really, really bad. But in fact, it was that next evening that I did the experiment that discovered superfluidity in helium-3. So failure might be an invitation to try something new, and that's what I did. Spend a little of your time doing something different. Curiosity-driven research is fun and can be rewarding. And so as a thesis advisor at Cornell University, I would come up with, what would happen if I did this? And then if I thought it was interesting, I'd go to the graduate student and say, what do you think would happen if you did this? And they said, we don't know. I said, well, why don't you try? And in fact, that's a very typical way of making discoveries. Avoid too many commitments. Now, I have to say that I was married by this time. My wife is Chinese, and she was working very hard to teach me Chinese, but I'm a very bad student. And so Cornell University was offering a course in conversational Chinese, and we both thought it would be great for me to take this course, but voila, I laughed myself to death. I realized that in fact I didn't have the time to take this course. So instead, I never learned any Chinese, but I did get a Nobel Prize. So that was the booby prize for not having gotten your first choice. Anyway, and then finally back off from what you're doing occasionally to gain a better perspective on the task at hand. And I think this is absolutely true. We become myopic when we focus too tightly on our work. And I don't know how many young people are in the audience, but I think it's good advice. Okay, so this is David Lee, yours truly, and Bob Richardson. You can't see mine very well, but I didn't bother doing that. They still gave me the prize, though, which is good. So now I go back to this Pomeranchuk cell, and I put the names of people who didn't necessarily give anything for making Pomeranchuk cells particularly, but in fact, whose contributions to science in general, without them, I would not have made the discovery I did. So Bardeen, Cooper, and Schrieffer were the ones that developed the theory that explained superconductivity, and that theory was then applied to helium-3 by Phil Anderson, a very dear friend of mine. And of course, Pomeranchuk's cooling cell was why I was able to get cold. But in fact, to use Pomeranchuk cooling, you actually had to get to very low temperatures. And I used a helium-3, helium-4 dilution refrigerator, which was invented by Edwards and Hall to do that. Bloch and Purcell, I used NMR extensively in my research, and thanks to Bloch and Purcell, NMR had been developed. And then Ed Hamel was the one that gave the world helium-3 by not throwing away this helium-3 that he separated from the tritium. So it is certainly not me alone that did this work. There were a myriad of people that were associated with this. And this is the way science actually works. And the wonderful thing about it is once the work is published, it's out there and anyone can use it in any country they want to use it. So science is, in fact, an international occupation, and it's something that's shared very, very easily and in a very friendly way between nations. So advances in science are seldom made by individuals alone. Let me make that clear. It looks like I did everything, but in fact, there are all those names up there. Those were people that gave contributions that I needed. They result from the progress of the scientific community, asking questions, developing new technologies to answer those questions, and sharing their results and their ideas with others. To have rapid progress, one must support. Now, this is for funding agencies, but I think I always have to remind funding agencies that they're important. To have rapid progress, one must support scientific research broadly and encourage scientists to interact with one another and to spend a bit of their time satisfying their own curiosities. This is how advances in science are really made. Thank you. But we're not done. This talk has basically two titles. One is how advances in science are made, and the other is how science changes our lives. And so I've gone back a long time. This is Nicholas Copernicus. He was born on 19th of February, 1473, so that was before probably any of us was born. Understatement for sure. But in fact, Copernicus was the person that first realized that it wasn't the sun that went around the earth, but rather it was all the planets went around the sun. So that was, in fact, one couldn't make a loaf of bread using that information, but in fact it really literally changed the way we thought about our part of the universe that we are inhabiting. Of course, Galileo actually supported this solar-centric model of the solar system, but he also did a lot of work in improving the telescope and actually then using the telescope to discover the first and largest moons of Jupiter. So these are people who, laid the basis for what we call modern science today. I love postage stamps, and I think this is actually a French, yes, you can see it's a French postage stamp, but in fact, the person they're celebrating is Sir Isaac Newton. Anyway, so Isaac Newton was born on the 4th of January, 1643, and died in March 1727. Oh, I would say, but it's true, that we perhaps owe Sir Isaac Newton more than any other early scientist. He developed the mathematics of calculus to understand particle motion and the idea of a gravitational field, thus explaining the motion of the planets. I mean, this was just remarkable work. It's too bad people don't live forever. So This is actually, so this is James Watt. Now, James Watt wasn't really a scientist. He was an inventor. And he used the science of heat, thermodynamics, in order to create heat engines, steam engines, which were vastly, well, a factor of 4 more efficient in terms of converting heat into mechanical energy. And so this is one of his heat engines. This is supposedly a picture of James Watt when he was a child. So he's playing at the dinner table. So if any of you have children that plays at the dinner table, keep in mind that you might have a James Watt on your hands. Okay, the trouble with steam engines back in those days is that the heat was provided by burning coal, and coal is never been a very clean source of heat. So this is billowing smoke coming from 2 rather high smokestacks, but in fact, I think London as a typical example of a city which was befouled with the products of burning coal for many, many years. And you know, it's not just carbon dioxide which goes in the atmosphere. Coal has a lot of other things, trace amounts of mercury and other things that you really don't want to be breathing in. And that's still true to this day, but in fact, this is one of the things that we basically have inherited, I suppose, from James Watt, and it's difficult to entirely get rid of the pollution caused by burning coal. The other thing, however, that happens when you burn coal, or almost anything else. So this is looking over the last 1,000 years, and this is the temperature, and there are fluctuations, and don't ask me how one measures the temperature, but in fact, there were actually some very good ways of looking at isotopes and things like that. And then starting about 150 years ago, the average temperature of oceans started rising. Here we show the CO2 concentration, which one can get by looking at bubbles in the Antarctic. And again, there's fluctuations, but in fact, at about the same point, in fact, the CO2 level in the atmosphere started rising very rapidly. Neither one of these things are very good news. The bottom line is, in fact, oceans have started warming, and the fear is, in fact, that this CO2 will stay in our environment for thousands of years. And so what we do today will have an impact not just on our children, but on our children's children's children. So I think it's very important that we take this seriously. Okay, well, so now we're going back in time, I suppose. I wanted to talk about a bunch of advances in science, or at least fields of science, that have actually done something wonderful for mankind. I would not say that the teeth of this dinosaur was something that was wonderful, but paleontology really, which is the study of bones of animals that lived millions of years ago, really gives us some sense for where we are as a people on a planet and what the history of that planet is. And I think it's very important that we do this sort of thing. We like to think of ourselves as owning the earth, but in fact, it is not just ours, it's ours to give our children and our children's children, etc., on into the future. So life on Earth and our place in the cosmos, the study of fossil remains of animals and plants that lived millions of years ago provides us with an understanding of the history of life on our planet. This is a story which helps us to better understand the origins and evolution of life on Earth, and also to appreciate the complex processes that produced the human race. This is one of my great heroes, James Clerk Maxwell. What Maxwell did was kind of interesting. The equations that described electricity and magnetism were pretty well established, but Maxwell realized there was one term that was missing, and when he put that term back in, what he found was, in fact, that electromagnetic waves would propagate in space and time. And now we understand that, in fact, electromagnetic waves include radio waves, microwaves, light, X-rays, and gamma rays. And that understanding really resulted from James Clerk Maxwell. This is another one of my heroes, I dare say. This is, of course, Charles Darwin, who visited the Galapagos Islands in 1835, and it was there that he developed his theory of natural selection, and ultimately wrote The Origin of the Species, published in 1859. And so another one of these people that I think had ideas which have really changed the way we thought about our place in the cosmos. This is another one some of you may think is more important. This is Alexander Fleming. He was born in 1881, and in 1928 he discovered penicillin. Now, specifically what he didn't invent penicillin. What he found, it was growing in a Petri dish, and as a result of the presence of the penicillin notatum, nothing else could grow there. And so that in fact made penicillin a very useful drug to counter disease, of course. Now, I put down on the bottom here, I've never been one that makes everything look like it's all good. Healthcare in the United States now costs $2.4 trillion. That was back in 2007, so it must be up to $2.6 trillion by now. It's a very expensive business. But in fact, we do have the possibility of prolonging life. So this is another one, and this is actually a very interesting story. This, of course, is the double helix DNA. This is where all of the genetic material in our bodies is, and how it needs to be, what it needs to generate, what pieces of this information one needs in order to build a human being. So this Nobel Prize, this work was given in physiology or medicine in 1962 to James Watson, Francis Crick, and Maurice Wilkins. Now, there was another person involved in this, and I wonder, does anyone here know who it was? Okay, good. I'm glad to know that she hasn't been forgotten. So this is Rosalind Franklin here. Rosalind Franklin actually did the X-ray crystallography on DNA that showed that it had this double helical structure. Sadly, they took them so long to give the Nobel Prize that she died before the prize was given. She was a young woman still when she died, and I think she definitely deserved to share the Nobel Prize. We're almost done here, but now we're getting to some pieces of work that I think have really changed our lives. This is the invention of the transistor in 1947. And the story is very interesting because AT&T, the telephone people, realized that the rate of growth of the number of electron tubes that they needed in order to run the telephone system was getting out of hand, to the point where they literally didn't have the money just to keep the tubes going. And so they went to John Bardeen, who was a brilliant theorist, condensed matter theorist, and suggested, I guess it was Bardeen and Shockley mostly, that they try to make an equivalent to an electron tube, but using semiconductor devices. And this is the first. It's sort of a bipolar transistor, but it's a sort of a weird mix of things. So as a result of the transistor, of course, rather than having this elegant telephone circa 1950, we have Apple iPhone Gs and things like that. Everyone has a cell phone of some sort right now, and it's thanks to Bardeen, Bratton, and Shockley. This is my computer. It's sitting over there on the desk. But it's basically 2.93 gigahertz Intel dual core processor, 8 gigabytes of RAM. I think the thing is lagged behind is hard drives. It's only half a terabyte hard drive, but that's usually enough for most of what I do. Okay, so now let's leave the planet for a minute. This is, in fact, the Hubble Space Telescope, which was launched April 24th, 1990. And really, you're up above the atmosphere. This is an extremely good telescope, and we can literally see more with this telescope than with probably all the other telescopes that have been put together over the years. Another interesting one is that NASA puts up satellites that don't look up and out of the Earth's sphere, but rather look down at the Earth. So this is one that's monitoring the CO2 content in our atmosphere. And you know, the news has generally not been very good in that regard. We have too much CO2 in our atmosphere. This, of course, is Mars, and of course, I don't think there's anyone whose imagination was not captured by Spirit and Opportunity when those two Mars rovers landed on Mars. Mars is, I would say, the planet other than the Earth, which is potentially habitable, but I personally don't think it's likely that we're going to be habiting Mars anytime soon. So I just wanted to remind you, I think this is the last slide. I was actually on the board that investigated the Columbia shuttle accident. And you look at this picture of a launch, I don't know which orbiter this was, but the solid rocket boosters, each one of these guys has 3 million pounds of thrust. The tubes themselves are 12 feet in diameter. It's a phenomenal technology was built up. The main engines on the orbiter burn oxygen and hydrogen. But this guy, because of the fact that the orbiter itself weighs so much, 220,000 pounds, I would say this was not a mechanical or a technical defect. This was a defect in NASA's management. I was on the board, and it was really sad. All right, and now I'm going to slowly go through this, and you'll see there's a little piece that popped up right there. That's a piece of foam. This stuff is 1/30th the density of water, very low density foam. And now we keep going, and it looks like it's going higher, but it's actually not. It's just the perspective. It goes underneath the left wing of Columbia, and then you see a bunch of spray coming out. Obviously, it struck something. And the question was, did it strike the leading edge of the left wing of Columbia, or did it strike the underside of the left wing of Columbia? And if it struck the leading edge of the left wing, that would probably mean that the astronauts would die on re-entry from orbit. Okay, so this is it, and I wanted to show you, get back to nature and enjoy the tall trees. Thank you very much.
Thank you. There'll be a question and answer session.
Professor Osheroff, may I ask for your opinions? We seem to be concerned about the planet and mankind. But you as researcher and scientists, you are working in the laboratories. What comes first, safety or the planet?
Well, okay, I think that safety and the planet go hand in hand, which is to say that I think if we abuse the planet, I think we are really abusing our future. And I dare say if I were a young person today, I would certainly be very happy to picket coal-fired. So I think it's a difficult question. And part of it, I think, gets back to the fact that the human beings have an enormous thirst for energy, and we seem to have a rather callous disregard for the well-being of the planet. Thank you for your question.
I have a question. You have mentioned many superheroes, actually heroes, scientific heroes like James Watt, Maxwell, Copernicus. My question is, when did you start having them as a hero? And how their work affect your inspiration in scientific careers?
Yeah.
Thank you.
Yeah, this is interesting. I mean, I thought of these people and realized that they had exciting lives and they'd made important contributions to mankind. And I suppose that as a scientist, I might have the opportunities to do that myself, but in fact, I actually did science because I derived a great deal of pleasure out of tricking nature into giving up her secrets. And this is what William Hawke, my chemistry teacher, said basically, that every time you do an experiment, you're asking a question of nature. And so when I think about doing experiments, what I think about is tricking nature into giving up her secrets by asking the right questions. And it's a lot of fun, but it really depends on who you are. I mean, I just love coming up with new ways of doing things, and I think a lot of physicists anyway do that. I can't speak for other disciplines, but I think for a lot of us, we're sort of, I think scientists in general tend to be fairly creative, and it's fun with trying to come up with new ways of getting nature to answer your questions so that you can understand what she's saying. And thank you.
Thank you very much.
Earlier you mentioned you compared research to like asking questions to nature. I was just wondering, as a scientist, do you think that there are some questions that we as humans, perhaps about the universe or existence, that we simply cannot answer? And if so, what do you think those questions are?
Well, I think there are the questions that we can't answer now. I mean, I don't know if that will always be the case, but for instance, I think our idea of what the cosmos is and how far out it goes and all that is, I think, changing as we get more information. And so, I don't like to think of science as something that's done and then it's sitting there cast in stone. In fact, it's a process of our learning about nature, learning about the cosmos and our environment and the oceans and all of these things. And I don't think it's likely that we'll ever run out of questions to ask. I guess I'm more concerned, in fact, about the quality of the answers that we get. But thank you very much for your question.
Thank you.
ศาสตราจารย์ดักลาส ดี โอเชรอฟได้รับรางวัลโนเบลสาขาฟิสิกส์เมื่อปีค.ศ. 1996 จากการค้นพบความเป็นของไหลยิ่งยวดในธาตุไอโซโทปฮีเลียม 3 ถือเป็นการค้นพบที่เป็นประโยชน์ต่อวงการวิทยาศาสตร์เป็นอย่างมากและก่อให้เกิดการศึกษาและวิจัยด้านของไหลยิ่งยวดซึ่งมีประโยชน์ในการศึกษาปรากฏการณ์อื่นๆในธรรมชาติเช่นการศึกษาการก่อตัวของกาแล็กซีในยุคเริ่มต้นของจักรวาลปัจจุบันศาสตราจารย์ดักลาส ดี โอเชรอฟอายุ 67 ปีเป็นศาสตราจารย์สาขาฟิสิกส์มหาวิทยาลัยสแตนฟอร์ด ซึ่งในครั้งนี้ท่านได้ให้เกียรติมาแบ่งปันความรู้และสร้างแรงบันดาลใจในการเรียนวิทยาศาสตร์และตอบคำถามจากนักเรียนโรงเรียนต่างๆทั่วประเทศ
Well, it's my pleasure to be here today, and I suppose this session is supposed to pique your curiosity, and so I should tell you some interesting things about myself. I was one of 5 children. My father was a medical doctor, and he was quite often patching me up after something exploded. I was very interested in high voltage electricity and gunpowder when I was your age. And we lived at the edge of town, so it was relatively easy to do things like this. I was into rockets and all sorts of other things, and I suppose I'm very fortunate to have survived my childhood. So I do not recommend that you do all the things that I did, because you have to be indeed very lucky to survive. So you heard that I did my undergraduate work at Caltech, and of course this was during the period of time that Richard Feynman was teaching the undergraduates.
Richard Feynman คือนักฟิสิกส์ผู้ได้รับรางวัลโนเบลเมื่อปี 1965 และเป็นหนึ่งใน 10 สุดยอดนักฟิสิกส์โลกตลอดกาลจากผลการสำรวจของ Physics World เมื่อตอนที่เขาเป็นอาจารย์อยู่ที่สถาบันเทคโนโลยีแห่งแคลิฟอร์เนียหรือ Caltech คุณ Osheroff ซึ่งเป็นนักศึกษาอยู่ในเวลานั้นจึงมีโอกาสได้เข้าเลคเชอร์วิชาของ Richard Feynman ด้วย
So everyone, even those that were majoring in fields like history, had to take 2 years of Feynman physics, which I think for some of the students felt that was cruel and unusual punishment. But I think most of us felt that Richard Feynman was our idol and our great leader. So Feynman, of course, was a very curious character. He described himself as being a very curious character. So he has all sorts of, he likes to do things unconventionally. And eventually I was being offered a job at Caltech. And so I took this opportunity to talk to Richard Feynman, and I said that someone at Bell Laboratories had suggested that he was going to host Feynman's visit at Bell Laboratories, that's in Murray Hill, New Jersey, in the summertime. And I said, you don't want to come to New Jersey during the summertime because it's very hot and humid like it is here, I suppose. So as if Feynman didn't know, he grew up in New York City, so he knew how bad it was. And I said, why don't you actually come in the springtime? It's a very nice time of the year. And so we sort of agreed, and then somehow I ended up being his host. And it's, of course, I was very nervous about hosting someone as famous as Richard Feynman. So eventually he said, at one point he said, all right, I'm Dick and you're Doug, and we shake hands and say, let's start out all over again. I'm just an ordinary person and you're an ordinary person, and we'll go from there. And so Feynman had brought his daughter with him, Michelle Feynman, and I was responsible for entertaining her somehow. And so I didn't know much about Michelle Feynman, except I knew she was very interested in horses. So there was someone at Bell Laboratories whose wife ran a horse stable for handicapped youngsters. Most of these youngsters were blind, I think. So it must have been quite scary to be on top of something as tall as a horse, but maybe in fact you didn't actually know how high off the ground you were. We showed him around to the various research labs, and he talked to a lot of people. And then it was time for his talk. And so, Feynman, first of all, the Arnold Auditorium at Bell Laboratories was completely packed. The fire marshals would have probably closed us down because there was no way for people to get out. All of the stairways and all of the pathways were all crowded with people. Then he started giving his talk, and of course, Feynman was, really interesting person. But what he talked about, I was very disappointed. He talked about reversible computers. Now, the thing about a reversible computer is for any process to be reversible, it has to occur slowly. Otherwise, for instance, if you're talking about having charge running on and off the gate of a field effect transistor, if the charge moves very fast, it dissipates energy. And so he was talking about processes that are very unrealistic in the sense that the last thing you want is a computer that goes very slowly. So I was very disappointed, but at the end he asked for questions, and the questions went on for 2 hours. And suddenly I realized that Feynman knew very well, much better than I knew, what his audience was interested in. These were all engineers that were in the process of making devices that used transistors in them. And so I'm glad that I didn't say anything out of turn. But Feynman was an interesting character, there's no question about that. There's a very interesting book, Michelle Feynman, who's Feynman's daughter, actually put a book together, and I can't remember the name of it now, but if you have a chance of finding a book written by Michelle Feynman, I think you'll find it quite interesting. Well, as I said, I grew up on, I would guess, mostly gunpowder and high voltage electricity. It turns out I grew up in a logging town in the Pacific Northwest, and in fact, my first summer job after I graduated from high school, I worked in a sawmill, and then my second summer and then third summer after graduating from high school, I worked in paper mills. So this was hard physical labor, and I suspect that most of you won't enjoy the opportunity of working that hard, hopefully ever in your life. There was one night when I was working very hard, I lost 10 pounds. It's all water because I was working so hard. But in fact, it was kind of interesting to see how people that didn't go on to universities worked. And it's not something that you want to do. That's all I can say. So look, I think what we should do is you know a little bit about me, so why don't we just open the floor to questions. You can ask me questions, and I'll try to answer them. Who wants to be first?
Hello, my name is Thanaplatin Yingtawi. I study in a homeschooling. And the question is, in the future, in 10 to 20 years, what science career path will be the most important? And if you have any chance to combine all three subjects in science?
Well, you've asked a very good question, and unfortunately, I don't think anyone really knows the answer to that question right now. But that's what I think. We have to look toward the future and see, try to anticipate. What first of all, what the opportunities are, because as society progresses, we come up with interesting ideas, and those ideas result in new technologies, and those technologies allow man to do new and different things. And so it's kind of very difficult to guess, what will be important and what will be available to us 20 years from now. So I can't answer your question. But I think it's a very good question, and I think it's something that we all want to look forward and try to anticipate what the future will bring. So thank you very much, and I'm sorry I cannot answer your question.
That's fine. Would you like to ask another question?
And in the past, science developed from the philosophies, but now science is gearing out and now because mathematics is gearing out from the philosophies, and is any way that the science will come back to the philosophy? Because now some people comment that it's start to come back to philosophies, and some people don't use mathematics in science.
Well, I think it's hard to do science without mathematics, but I think what you're talking about is what I would call natural philosophy, and I think I will give you the answer which I suppose my high school chemistry teacher would have said, something like that. He came in class one day and he had a milk carton, and there was something inside the milk carton, and he said, every time you do an experiment, you're asking a question of nature. Nature has to answer your questions, but nature's answers aren't, and then he shook this thing, said, what's in the milk carton, but rather something about what's in the milk carton. And so then you have to ask nature another question. And the idea is to trick nature into giving up one of her secrets. And in fact, I will show you a picture of my chemistry teacher. Sadly, he died before I got the Nobel Prize, but in fact, he was, I think, one of my great heroes. And I think the way he thought about doing research is the way I still think about doing it today. Thank you. That was a wonderful question.
At the present, physics technology have far beyond from the past. So we all know we have discovered the Boston particle, stuff like that. And so what I want to know is, what is now the ultimate challenge in the physics that now face?
Oh, well, I think the physics is a rather broad field, and I don't think there is a single ultimate challenge. I think, of course, the big challenge was to discover the Higgs boson. That was the challenge that the high-energy particle physicists have been faced with, and of course they did discover the Higgs boson. What that does for mankind, I think, is really not clear, because it was very expensive building the accelerator, allowed scientists to produce the Higgs boson, and it's not something, it doesn't last a very long time. It has a short lifetime. So it's I think it confirms that the particle theorists really understand at a fairly deep level that kind of physics. And I think it wasn't clear at all to a lot of people that they would ever see a Higgs boson. And as soon as they saw a Higgs boson, I think everyone decided that it would probably have been more interesting if they hadn't seen the Higgs boson. So that's just one piece of physics. I think if you look in my field of condensed matter physics, what's really big right now is nanotechnology. And we call it technology, I suppose, because it gets more funding research if you call it technology than if you just call it physics now. But in fact, there's a lot of very interesting physics which one can do with very tiny particles, things that you can either make. Obviously, the smallest particles we have are individual atoms, but I suppose if you tear an atom apart, you have electrons and protons and all sorts of things in the nucleus of the atoms, but those are generally not very stable. But certainly you can talk about making something on the nano scale, and in fact that's been going on now, I would say, for at least 20 years. There's some good friends of mine at Bell Laboratories, in fact, were involved in that. There's a guy named Dave Bishop. Now sadly, Bell Laboratories, which I think was the greatest research laboratory in the world, doesn't exist anymore. So in fact, no one's doing those sorts of things at Bell Laboratories anymore. But there's a lot nanoscale physics that is going on. And I think the idea is that one can ask a question, and then in fact you are driven to create a technology which will help you answer that question. And frequently in the process of coming up with new technologies to answer some curiosity-driven question that you might have come up with, in fact, you, not by accident, but as a product of your research, end up developing a new device or a new technology which has many other uses for mankind. And in fact, when I give my talk later on this morning, I will point out some of those cases where new technologies have resulted from curiosity-driven research.
Why do you like to study physics? Why not biology or linguistics or any other field? Do you have any special?
Wow, that's an interesting question. I suppose that when I was very young, in fact, I think I was 6 years old. For Christmas, I got an electric train for Christmas, and that usually my father was a medical doctor, so he spent a lot of nights at the hospital, and so he would take a nap every afternoon. But while he was taking the nap, I tore apart the locomotive because I was very interested in trying to understand how electric motors worked. And so then he woke up and he saw that I'd torn apart this toy that he'd given me for Christmas, and rather than scolding me and sending me to bed without my supper or something like that, he was rather fascinated with my fascination for things electrical and magnetic. And so he would bring things home that his patients had given him. And frequently I was able to make these into, shall we say, nearly lethal toys. He brought home some parts from the telephone company. He had a patient who worked for the telephone company. And so it had a solenoid actuated relay, and I took the two leads from the solenoid and connected them to a 22-volt battery, and when I removed the leads, I got a good healthy shock. And of course, I think probably most of you in this audience, I hope, would understand what happens, of course, when you interrupt the electrical current flowing through the solenoid. The magnetic field very rapidly decreases to zero, and as it does that, it induces a voltage across the coil. And of course, you have a lot of turns of wire, you end up getting a pretty good shock. So I took this thing to school the next day, and the solenoid and the battery were in a duffel bag. And then students, and all that came out was a lamp cord, the sort that you'd plug into the wall. And so students would squeeze the two prongs together, and when they released them, they would get shocked. So I'm very lucky that I actually didn't get kicked out of school for that. But well, we've gone pretty far. What was your question, by the way?
So I think that answered my questions.
Okay.
Already. Okay. But try not to do that at home, right?
Well, I don't know. I think within limits, okay, you can do these things.
Okay.
But, this curiosity-driven, I was doing curiosity-driven research at that point, and I dare say, I think that a lot of research is curiosity-driven research, and in fact, I'll show some examples of where our curiosity-driven research has resulted in devices that are very beneficial to mankind.
Yes, I interest in your answer, and I think, what the difference of physics and engineer? Yes, it's just the same. I don't know what the difference. Just.
Yeah, I agree with you entirely that of course, there's a lot of different kinds of engineering. There's chemical engineering, there's biomechanical engineering. They're all sorts of different. But in fact, I think the main difference between physics and engineering is simply, in fact, what one could a lot of it you could say is applied physics. Then that's really engineering. And a lot of my friends at Bell Laboratories were doing exactly that sort of thing. They were developing new technologies to allow them to probe nature in some new and different way. Some of those cases, in fact, that forced them to develop new technologies, and some of those technologies are being used by the telephone company even to this day.
When you was young, have you ever think before someday you will get a Nobel Prize, and what is make you be successful? Thank you.
Good question. That's a really good question. And the answer is no. But I think that I should add a PS on to the no, and that is I think those people that actually pursue a career with the expectation of winning a Nobel Prize, most of those people end up dying as very disappointed old men, because most of the people that have that attitude are old men, I think. So you know, I think that the people that are most successful in science are those people that have a passion for understanding things, and have a deep curiosity about how nature behaves, and so then they come up with new ways. And I'll talk about some of that when I talk about nuclear magnetic resonance, which is one of my favorite ways of probing matter. So, but the answer is, I think there are people that go in with the idea of winning a Nobel Prize, but I certainly don't regard that as being the proper motivation. I think what you really want to do is understand something about nature that no one has ever understood before. And I think that's very positive, and it can certainly be very motivating. But I think those people that are looking for Nobel Prizes, probably most of them will never see a Nobel Prize. Knowing at some point that you might win a Nobel Prize is actually very unnerving, because most of us have very full and exciting lives, and the idea that you're going to win a Nobel Prize, it really, I can tell you, it really does change your life. And in ways, some ways that are good, like I get to do a lot of travel and come and meet a lot of different people all over the world. But at the same time, I'm doing that at the expense of not being able to do the research that actually got me the prize in the first place.
From that question, from the former question, so how is your life after you get the Nobel Prize? Maybe you are like a celebrity.
Yeah. Well, okay. I think you know some of the answer to that. I mean, once you get the Nobel Prize, everyone wants you on their advisory board. Whether you have any advice to give, if it's some area that is completely so far removed from my area of expertise, but they still want me on their advisory board, so they can use my name. They don't necessarily use my advice. But you know, I think the thing that I enjoy doing the most is this kind of thing, where I sort of do a lot of international travel, and I make a lot of friends. I hope I can do that here, and part of it is, of course, this business about stimulating young people to think about careers in science, because I think it is important. So I don't know if I've answered your question, but so what happens is you ask me a question, and that stimulates me to reply, but not necessarily to your question.
You know that a lot of history scientists, they like have to change everyone belief and something like that. Is it hard for you to think in different way, something like that?
Well, I think, yeah. I mean, as a scientist, I think, you know, you're really in pursuit of an understanding of nature, and And I think at some point you're doing an experiment and you think you know the answer, but then you do something, you find, well, that's completely wrong. And so then you have to start thinking differently than you were before. And I think that's, you know, it's kind of this fun game that scientists play, that they try to trick nature into giving up her secrets. And that's exactly the way my chemistry teacher described it when I was in high school chemistry class.
Do you not feel tired? Like, it's fail every time. Did you feel something like
Well,
that?
if you fail every time, I suppose you should think about something else to do. But I think, you know, it isn't that you always fail. You don't always fail. You kind of, you do learn from your mistakes. I think we all do. And so you, for instance, do an experiment that doesn't work, and then you say, okay, what did I do wrong? And then you try to do it again, and it's this. I still think of it as a conversation that I have with nature. Nature is a woman, of course. We all know that Mother Nature, right? And so if you ask a woman certain questions, such as "Will you marry me?" You really don't understand the answer. So then you have to ask other questions, and that's the way. And each time you do an experiment, you're asking a question of nature. So I'm not going to marry Mother Nature. I'm already married. Okay.
What would you say is more important between pure science, the branch that deals with only theories, and applied science, like medical doctor, engineering, something like that? What would you say is more important?
It's hard to say that one is more important than the next. I think certainly, you know, I think bioengineering and these are very closely related to medical applications, and I think we would all agree that something, for instance, which will allow someone that is blind to, at some level, see, that's an important thing.
So what you're saying is that they help each other, they support between each other?
Oh, absolutely. I would not say that all science is done with the expectation of producing new ways for blind people or for deaf people or whatever to hear or see. But in fact, there is, I think, people that are straddling the border between applied medical applications for science and those that in fact are developing the new technologies to probe nature. And I think that it is wonderful when those two purposes come together and in fact you do something which such as allowing blind people to, quote, see. Of course, they're not seeing, but they get a very good idea of what's going on around them and stuff like that. When I was an undergraduate at Caltech, I actually was dating a blind girl. So I know a little bit about that. Actually, she was one of identical twins. And back when, you know, I was born and she was born, so just around the end of World War II, when usually if you had a multiple birth, such as identical twins, the babies would be put in an oxygen tent. And if you don't regulate the percent oxygen carefully, in fact, you would probably blind the infants. And that's what happened to both of these girls. Because they just weren't ready for that. So it's very medical applications of science are complicated, I think, and we certainly learn from our mistakes, but I think that some of those mistakes leave people blind or deaf, et cetera, et cetera.
Thank you very much, Professor. And can I have one extra question? From a scientist, do you really think that the world is gonna end something?
笑死我了. I laughed myself to death. No, I don't think that the world is going to end in another week or another year. Or let's face it, the world has been around for billions of years, and I see no reason to suspect that in fact it won't be around for billions of more years. Now, that said, I think that human beings, by the activities that we do, I mean, in particular, I think burning fossil fuels is having a very profound impact on our planet. And I don't think that is going to make the planet go away, but in fact, it certainly has the possibility of impacting a lot of species may disappear as a result of our changing their habitats. Of course, if you put a lot of CO2 into the atmosphere, then it's much more difficult for the infrared radiation to leave the planet, and that's part of global warming. So, I think we, as I like to think that we are occupants of this planet, but we don't own it. And I think we have a responsibility, not just to ourselves or to the planet, but to the future generations, which certainly don't want to inherit a dead planet. So, you've brought up something very interesting. Thank you very much.
Thank you, sir.
That's cheating.
Well,
no.
Well, he's well prepared.
I'm a student who is interested in studying physics, but unfortunately, I always fail in any test. How do you think about this way for solving this problem?
So,
that's tough. I have to say that I think I've kind of been in love with Mother Nature in some sense. Ever since I was probably 6 years old, and I think I became, even irrespective of the science that I learned in school. In fact, I think I learned more science probably through middle school anyway, on my own than I did from the classes I took. So I think the thing that makes you a good scientist is curiosity and a love for the subject. And the last thing that is likely to make you a good scientist is the fear of failing an exam. So I think what you need to do is just do reading on your own. I mean, certainly there were a bunch of kids and myself that we formed kind of a loose club, and we would talk a lot about science, mainly physics. But I think you're really you learn faster and better if you ask the questions rather than if someone else asks the questions. And so I think to become a good scientist, you start asking yourself questions. Okay.
Thank you very much.
Thank you.
So, as you mentioned lastly about the curiosity, I would just like to ask that Thai students tend to be to cram things in their head rather than participating in discussions and volunteering. So that's why it's less productive to produce scientists in Thailand. What are some methods to induce young scientists or young Thai students, especially the schoolings, to the term curiosity and inducing them to curiosity?
Yeah,
Thank
well,
you.
that's You're asking a very good question. And I mean, I think it takes a strategy of, posing a question to students. I personally, think that the best learning I've ever had before I got to Caltech was probably in my chemistry class, where in fact we would be small groups, and the teacher would ask some question, and we would argue amongst each other until we felt we understood what the answer to the question was. Of course, sometimes we weren't right, but in fact, I think this business about being self-motivated and being in a small group of where you're motivated by your peers rather than being motivated by the fear of getting a bad grade in class. I mean, that's of course, it's an effective technique, but in fact, I don't think it's as valuable as self-motivation is.
Before you got the Nobel Prize, have you ever known that the thing that you think can possibly to change the world?
Well, I don't know that anything I've done has really changed the world, but I do things mainly because I enjoy doing them and because I'm good at it. The things I'm not good at, I don't do. So I dare say I took art lessons when I was young, and I was terrible. And so I had this choice. I could either take swimming lessons or art lessons, and that was a very easy choice for me to make, because it was the art lessons. I was very bad at art, and so I think we're all, each of us is the manager of our own human resources, and I think you have to know what motivates you to begin with, what those things are that you are good at, because they're usually the same things that you enjoy doing, and then go from there. But I think that's the worst thing to do, is to hammer your head against a rock expecting the rock is going to crack, because it's your head that's going to crack first. So what you really need to do is understand who you are, what motivates you, what you enjoy doing the most, and then find out how you can use these very powerful and very positive emotions to do something that might in fact be useful for other people besides yourself. So thank you very much.
Have you ever seen the movie named A Beautiful Mind? Yeah, it is about John Nash life, yes. and that movie show how the curiosity of him to mathematics, how strong of your passion of his passion to mathematics. So I wonder that in your mind, yeah, is your mind like John Nash is your? Oh, I'm sorry, I'm not, and that doesn't mean that I'm just want to know that how strong passion that how strong of your passion to physics, how deep curiosity you have to physics.
Yeah, well, that's a complicated question. I think, well, first of all, John Nash was, I think, primarily a very good mathematical economist, and that's not something that I'm likely to do. So there's a lot of difference between us. But and of course, Nash had all sorts of other problems which he overcame, really quite remarkably, and ultimately I think ended up contributing in important ways to mankind. Now, I don't know whether I've done that, okay, but I try. I think that we, what's true is that we're not all going to all of a sudden come up with some brilliant idea which is going to change the future of mankind. That's unlikely to happen. But I think, you know, what you can do, first of all, I think, you know, you want, I think we all need to be needed, and you want to do something which will benefit not just yourself, but your friends, and basically mankind. And so I think as you're going through school, you know, you can see those areas, the big questions, and you can say, is this something that I can contribute to, and something which I can enjoy doing. And you know, I think for all of us, we all would like to think of ourselves as contributing, and in ways which are non-trivial and possibly important. I think it's really worthwhile to look inside yourself to understand what your motivations are, what your emotions are, because it's funny, we all think that emotions are not very good things. They don't have anything to do with science, but in fact they do. Because it's emotions that drive us to do the things that we do. We asking nature the very difficult questions. That's an emotion drives you to do that. And so I think those people that end up being most successful in science are the people that start out knowing a lot about themselves, what motivates them, and what allows them to succeed even in the face of failure, because that happens to us a lot. So, good question. Thank you very much.
Good morning. I'm Vacharaporn. I'm a mom of this little boy. We take him out of the school since grade 3 because we have learned that he has multiple abilities. He's also good in violin, in painting, and best of all, he's motivated himself for science. Right now, he developed his science ability very high. But my point as a mom and conducting homeschool, what I would like to ask you is there anything that we have to worry about? Because it seems that he learned a lot by himself. And is there any consequence, because he's not in the schooling system, so is there any chance that the way that he learn is the jumping from one thing to the other, or the subject is not followed by the curriculum? Is there any chance that we will miss anything along the way, or anything that we should be aware of in order to support him, and then he can make all the biology, he loves all the biology, physics, and chemistry, but he still cannot decide which one he loves best in order to go like that. Is there any chance or anything that we should think about in order to make him be successful as a scientist in the future?
Yeah, that you're asking a set of very complicated questions, of course. I think that first of all, when I was junior high school, middle school, or something like that, you know, I had a set of friends, and we tended to, we were the science geeks. I don't know if that's a word that means anything here, but I mean, we were the kind of the sort of people that were more interested in science, I suppose, than in girls. There you can see where we are. But I think we were, you know, because, you know, I think it is very important that we all develop good interpersonal skills, that we can interact with people effectively and positively. And I think, you know, my personal feeling is that I'm happy that I had these friends in school, because in fact that, I think, allowed me to develop these interpersonal skills. And I don't know if that's an important issue for you.
In terms of the social life, I don't worry much about him, because he is very sociable. He go everywhere and can make friends easily.
That's good.
But my point is the way he study, because it's not by the curriculum, not the step by step.
Okay.
but he learned so many things by himself. So what I'm worried whether the way he process, the way of thinking, is there anything that I have to worry about the consequence in order that he know have the good foundation in order to develop up into the complicated things in the future?
Yeah, I mean, certainly I think it doesn't hurt anyone to have a mentor. So where, you know, someone who's looking over your shoulder and seeing whether you're doing things going in productive direction or not. And so I think certainly when I was in high school, I had people, teachers that I think fulfilled that role for me quite effectively. I don't know, it's tricky. You know, my father actually was quite interested in science, and so he sort of would bring things home. I would say I am lucky to have survived my childhood, but you know, I think it does help. I think having if you have a really good teacher who can understand, you know, the passions of young students and also the needs. So, and I don't know whether public school is well equipped to provide you know, those essentials, which you know, a student who's very bright and maybe well ahead of the rest of the class. So the answer is, I would think that a good teacher is a good friend.
Good morning. This is the same question. I am the dad of this boy. Besides from the science curriculum, in the normal curriculum, he have finished it all by himself, read it through, and then after that we connect right to Mahidol University and to send him to enter the laboratory with some mentors, graduate students, and then he also joined the class in Mahidol University. I wonder whether this is the correct way to have the productive output, because it jumped too fast or not.
Yeah. Oh, well, this is the classic conundrum now that you are afraid that the student will learn too fast and maybe end up with gaps in the education or something like that, or you know, look, I think that smart people, smart children, have a lot more flexibility and capability than we give them credit for, particularly when it's, I think, things that we don't control, the way they think about things and stuff like that. But I think in general, it's probably more important to expose bright children to interesting ways of thinking about things rather than worrying that they need to learn everything as everyone else is learning it. I think that's a mistake. So maybe we can talk at some later time about this.
Thank you, Professor.
Someone tells me that physics is king of science. How about your opinion?
Well, I think physics is actually king of science. Look, I think for me, physics has been spectacular. I enjoy physics very, very much. I like to think about it rather deeply. But you know, I think we're all different, okay? And I think there are a lot of people that would claim that biology is more fascinating and more interesting and more relevant. And you know, it really depends on who you are and what your interests are. So I think physics actually has a lot to contribute to the other sciences. So for instance, a lot of NMR was developed by physicists, but in fact it's used for biomedical applications all the time now. And so I don't know, I think there is some physics, I think, in almost everything that we do. And I like to think that physics is important for that reason. But if you talk about, and I dare say, if you look at chemistry, if you look at chemical processes, it's really not very different from complex systems thought of from a physics perspective. You can essentially do that. So I think physics is important, but if you look at these other sciences, I think chemistry ends up being, the way chemists think about their subject is I think much more effective than if you start from the beginning and think about it as from the physics perspective. And then, of course, you have biology, and I don't know if you want to worry about, I think now, I'm certainly, I don't know about other people in this room right now, but I'm very concerned about the health of our planet. As you can tell, the atmosphere, the oceans, there's a lot of, the ecology has become a very important science. So I don't like to say that one science is more important than any other science. They're different, and I think if you're thinking about what science you would like to pursue a career in, then I think you have to know something about a whole bunch of different sciences and a lot about yourself before you make that decision.
Yes, thank you.
Thank you.
Thank you, yes.
I think the people that are most successful in science are those people that have a passion for understanding things and have a deep curiosity about how nature behaves.